206 5-minute exposures, 17 hours of total integration, 7 nights over 7 weeks. This is NGC 1491, the Fossil Footprint Nebula, and this is how I turned 206 raw frames into this final image using PixInsight. My name is Morten, and you are watching Frost Astrophotography. Over 7 nights between September 24th and November 13th, I captured 206 light frames of NGC 1491. Each exposure was 5 minutes long, using Narrowband SHO filters on my Player One Poseidon M Pro monochrome camera. 70 frames in hydrogen alpha for the nebula structure, 66 frames in O3 for the ionized core, and 70 frames in sulfur 2 for the outer detail. This near equal distribution is ideal for SHO palette work and shows the importance of planning your filter strategy before you even start imaging. NGC 1491 sits in the constellation Perseus at magnitude 11.2. Most astrophotographers capture 8 to 12 hours total on this target. I pushed to 17 hours, specifically to reveal those faint outer extensions beyond the bright core, the parts that give it that distinctive footprint shape. And here's a fun fact: that footprint shape isn't just visual coincidence, it's actually a wind-blown bubble created by the central star BD plus 5886. I captured this with my Skywatcher EvoStar 80 ED paired with the Player One Poseidon M Pro monochrome camera and SHO narrowband filters, all mounted on my belt-modded HEQ5 Pro. So why 17 hours? With 66 to 70 frames per channel, my signal-to-noise ratio is excellent. This means cleaner stretching later and the ability to push the data harder without introducing noise artifacts. Alright, let's jump into PixInsight for some processing of NGC 1491, the Fossil Footprint Nebula. I have already completed the pre-processing of the light frames that we are going to use today, but I have tutorials that you can watch if you want to look more into detail on how you go about doing that. I've gathered all my approved light frames, and then I used the process star alignment to register all my light frames, making it possible to stack them on top of each other. I've also completed the stacking of the master light frames for my 3 filters. So you can see here that I have my S2 and my H-alpha and my O3 master light frames. Before proceeding, I like to do a dynamic crop on my light frames just to eliminate the outer edges of the light frames. The data quality is often worse there, and maybe we can see it if we zoom in. It wasn't that visible on my H-alpha, unfortunately, but sometimes it's very visible, and you do want to crop that out. So start with a dynamic crop, put it on one of your light frames. Make sure to drag the edges in a little bit like this, and then you can copy this crop to the other two or more if you have it light frames by dragging the triangle here onto the other two before accepting the third. This way you end up with the exact same crop on all three of the light frames. Now we're ready to proceed in the linear processing phase, and we have to do something about the background. I don't have that much gradients here. There's no big problems, but I usually use some kind of background extraction just to separate the nebulosity from the background. In this case, I'm going to use dynamic background extraction. So I'm going to put some of the control points here in this image on areas that I know are background. And make sure you don't put any of these samples on nebulosity that is faint or on a star, for example. So I'm going to put a few in here. You don't need a ton of these, but a few will suffice. And then we're going to save an instance of the dynamic background extraction to be used on the other two frames here, giving us an identical extraction. So grab this triangle and make a copy of this process, including the samples here, before accepting this background extraction. And then you can close this view. We'll minimize this for now and open it. On the next filter, accept the extraction, close it, and minimize. We can close the O3, and then we'll take the last filter, apply the same dynamic background extraction on that as well, and we cancel that active window. So now we have three new versions of our master light frames. I'm going to do a screen stretch on them, and now we have done the dynamic crop and the dynamic background extraction, and we are ready to proceed with the next step here. For me, that is blur exterminator and noise exterminator and star exterminator. For blur exterminator and noise exterminator, there's no built-in batch feature. If you have a lot of light frames that you want to run that on, you could make your own batch processing using process containers, but for now, I'm simply running blur exterminator and noise exterminator on all three. And then I will be running star exterminator on a batch processing. Now the blur exterminator and noise exterminator is complete. I can start star exterminator, and then I will select the process batch and simply select the output folder, and then click on select input files and execute, and you simply select the three files that you want to run the star exterminator on, and simply click OK to start the processing. Now the star exterminator has completed, and I'm sitting here with three starless versions of my SHO filters, and they are ready to be stretched. These are just screen stretched right now. If I remove the screen stretch, it will be completely black here. If I apply it, it will be a bit overblown maybe. So we carefully need to stretch these images without blowing out the highlighted areas, while revealing as much as we can on the outer areas here that actually contain data that we want to keep. Notice how each filter captures the different aspects of the nebula here. In the hydrogen alpha here, you can see a very strong nebula structure, and you can clearly see the fossil footprint visible in the middle here. In the oxygen 3, you see the highly ionized oxygen in the central parts of the nebula here. Oxygen 3 is typically the faintest signal, and it requires a lot of integration time to reveal its structures. The sulfur 2 channel reveals those subtle outer filaments and shock structures. This is the channel that really defines the footprint shape when we combine everything. You can choose a lot of different stretching options here. The easiest one is to simply copy the settings from the screen transfer function onto the histogram transformation tool, but that won't give you the best result in my opinion. I would suggest using the generalized hyperbolic stretch here and then gently try to bring those details out. I usually start with a very subtle stretch curve. I will mark my symmetry point here at the peak of the histogram or to the left of it. I won't set any intensity. I will simply just put in a stretch factor that gives me a subtle curve like this. Then I will repeat that stretch until we start to reveal some information in the nebulosity here. When I see that I get some, and especially in this case where you have some highlighted areas in the middle that are in the risk of being overblown, I will stop that stretch, and then I will put my symmetry point somewhere around the very faint details in the image, like that. I will send that to SP. I will set a fairly moderate local intensity, and then I will protect my highlights with the lever in the bottom here. Fairly aggressive, I would say, to make sure that we don't overblow the highlighted areas here. And then I will choose a stretch factor, revealing those details. Now it's simply a matter of iterations here to reveal more and more of the details here, maybe introducing some contrast in the highlighted areas here, and once in a while also select the linear mode to reset your black point a little bit. Making sure that we have a fairly good reading for the black point here, not too far from the left, but not all the way to the left, I would say. This is repeated for all three filters, and of course, if you watch my SHO processing guide, I will go into more details about the stretching process. We also need to stretch the stars, of course, because now they are separate from the nebulosity, and this is also done with generalized hyperbolic stretch. Open up the strongest signal for this object. It wasn't that big of a difference, but for some other you could have a much stronger signal in one of the light frames or in one of the filters, and you should use the strongest one. For the star stretching here, you don't need to set a symmetry point. Simply put your local intensity to the maximum value and open up a preview and simply stretch until you are satisfied with the stars here. I usually don't want the stars to be that prominent. I will zoom in on the strongest star here and adjust my stretch until I get no artifacts whatsoever, and to the point where I'm happy with the stretch. So that could be a good starting point. I will close this preview, and then I will simply take this stretch, apply it to all of my 3 filters, and now I have a star version for all 3 filters that I can use later in the process. Now for the magic moment, it is time to combine these monochrome SHO filter masterlight frames into a color image, and I'm using pixel math, and I'm assigning red to sulfur 2, green to H alpha, and blue to oxygen 3. Now this is the standard Hubble palette, and for this to work you simply put the name for each filter in here, and then we execute, and the PixInsight will combine this image for you. I will do the same exercise for the stars here that we stretched earlier. So take your HA03 and S2 stars, and then I will open up a pixel math once more, but this time I will be using a more advanced formula to composite the RGB color image. I have an in-depth video about how to do synthetic RGB stars, but this formula will basically take 40% of HA and 60% of S2 into the red channel, 40% of O3, 30% of HA, and 30% of S2 in the green, and 100% of O3 into the blue, and that will mix the stars here into as close as RGB or true color as you can get, and then I will run through the image solver on this image, and when that is done, so PixInsight knows where this is taken in the night sky, I can run through spectrophotometric color calibration on the stars here, making them calibrated to as close to RGB stars as possible. For the non-linear phase, it starts with color adjustments, and we do need to make a lot of color adjustments because right now, since we assigned HA into the green channel, and there's an abundance of HA in this object and most other objects, we have much more green than we have red and blue, and that's why we get this green image. I used to recommend running SCNR like many other people, but that is a very destructive process this early before any color adjustments whatsoever, so I avoid using that now, and instead I will adjust colors here in this image using masks and curves. For color masks, I can use the color mask script, and I can say that I want a green mask, and it will produce a green mask. You may want to add some convolution to the mask before using it, blurring it out a bit so you don't get sharp edges, because that could affect the overall image. So we apply a little convolution. You can save that on your workspace because you're probably going to be iterating and remaking a lot of masks. We put that on, and you can disable show mask so you can actually see what you're doing. Then we are opening up curves transformation here and a preview. Select the green color, and then you can start to slowly manipulate your green here. But as you notice, when we are decreasing green, you might want to increase others as well, because you're actually pulling down the brightness of that color. and we end up losing a little bit of brightness in the actual image here. So a better approach to this, when we have an image that is very overpowered by one color, like in this one, is that we can use the selective color correction script. So you can remove this mask and we can start the selective color correction that is included in the toolbox. And now we can select green once more. We can show mask here. You can see that we have a fairly similar mask in this tool, but here you can manipulate a lot more of the colors. So you can pull down green, for example, but at the same time you can increase the yellow, or you can increase yellow and red, for example. And also if you want to increase the blue a little bit here. And that way you can iterate your way forward in increments until you're happy with the final result here. This is my result after doing the initial color adjustments without using SCNR whatsoever. The image on the left here is the first that I started with. The image on the right here is the image that I ended up with after all of my color adjustments. Now, this adjustment included manipulating all of the colors basically. I also added some luminance to the shadow areas of the image here, and I increased the saturation and vibrance a lot for the entire luminosity in the image here. Next step was to sharpen the image a little bit, but as always, the sharpening is very subtle. You can see here the difference between the two. A slight sharpening of the image here on the right, not to sharpen too much. The telescope that I'm using is not a super sharp and expensive one, so there is a limit to what I can do with my gear right now. Next step is to run some noise reduction, and I usually just run through Noise Exterminator again on the Starless version. You can see here that we have a lot of noise left, especially in the darker areas, and with the Noise Exterminator you get a very good result without using more advanced measures that takes a lot of time, and in my opinion maybe does not produce the same good result. And as a final step here in the Starless processing in the nonlinear phase, I added a synthetic luminance layer just to increase the contrast here and also sharpen the image just a little bit more before moving into the final integration phase. Now we have two finished images here, the Starless version and the Stars version, both processed in the non-linear phase and ready to be integrated together again. The stars, I simply added a little bit of saturation and vibrance to them, even though you can't really see that when they are zoomed out like this. But they are still color calibrated, taking them as close to real RGB stars as possible, without taking any RGB frames whatsoever in this session. It's time to join the stars and the starless images here, and we take the trusted old pixel math, put in this simple formula, execute it, and then we get the final result. Now, it is usually time to do some final small adjustments, and of course I also did that this time. A slight S-curve to increase the contrast, maybe a little bit on the image here. And here is the final result. 17 hours of integration, 206 frames, 7 nights of imaging, all coming together into this view of NGC 1491, the Fossil Footprint Nebula. Thank you so much for watching this video, and as always, if you like it, please give it a thumbs up and consider subscribing if you're not already doing so. Until the next video, I wish you have clear skies.